Hello, Calculus and Vectors class. This is 5.6 optimization. Again, we're going to kind of switch gears and we're going to try something totally different, but it's another very useful application of calculus. Essentially, what we're doing here is we're going to take real world problems and we're going to see if we can use calculus to help solve them. So essentially what we're doing, we're going to be optimizing, which means we find the maximum or minimum value for a particular problem. And again, we know that if we have a function, if we can express something as a formula, then we can find the maximum or minimum just by saying the derivative equals 0. So seems like that would be very, very useful in the situation. It seems like a pretty straightforward, seems very easy in principle. But as we get into some problems, it gets a little bit tricky. But as long as you have a bit of know-how and can think outside the box a little bit, it's not too bad. So I have a bit of a rundown here of some strategies that can help you. I encourage you to read through those, but I find it best just to jump in and try some of these problems. So we're going to do that. So let's take one. Let's start with example 1. A farmer has 800 meters of fencing and wishes to enclose a rectangular field. One side of the field is against a country road which is already fenced. The farmer wishes to enclose a maximum area using all of his fencing. Find the dimensions that will produce a maximum enclosed area. So what I will start by saying is, it looks like a word problem, and you guys are probably experts with word problems. And in fact, it's very, very similar in terms of the way that you solve it. You start by reading the problem, identifying the key information, figuring out what you need to solve for, solving it, and then putting a therefore statement. But there are a couple of little differences as we go along. So the first thing that I want to point out, normally you have just one thing that you're solving for. So optimization problems are a little bit different in that you have something that you're solving for, but it's not always what you're optimizing. So my first thing that I say to students is always ask yourself 2 questions. Number 1, what is the problem solving? 2, what do we need to optimize? So in this one, it says find the dimensions. That seems like it's what's asking for us to solve for. So we're going to find, in this field, we're going to find the length and the width. But it's not what we're optimizing. So to find out what we're optimizing, we have to take a look, and we have to look for some keywords. So stuff like maximum or minimum. In this case, it says maximum enclosed area. So it seems like the area is the thing that we want to find the maximum value. So we're going to optimize the area. So that means that we're going to have to create a formula for area to represent this problem here. So let's start by taking the formula for area. Since it's a rectangle, that should be pretty simple. So it's just going to be length times width. Now here's the rub. Here's the problem. With calculus, with our differentiation, we only know how to differentiate formulas with one variable. So since we have length and width, this is not going to work for us just yet. So we have to use a bit of know-how to help us out and help us to make this a little simpler. So let's take a look at our problem again. We have our length and our width that we're solving for. And we said the farmer has 800 meters of fencing. So that's going to be important, 800 meters. It also says that one of the sides is already fenced because it's against the country road. So we're not going to worry about that. So we have to split up that 800 meters across the other 3 sides. It makes sense that we're going to use all of it because otherwise we can't have, if we don't use all 800 meters, we're going to have a smaller fence anyways. So we have to use all of it. So 800 is going to be equal to L plus 2W. So now we have that, and you're in the back of your mind, you're probably seeing that we have L's and W's, and you're thinking we can probably do a little bit of substitution to help us. And as a matter of fact, we can. So what we're going to do is we're going to take this equation that we just found and we're going to rearrange it so that way we have one of the variables isolated. You can do whichever you want, but I'm going to tell you right now that L is simpler, so we're going to go with that. So move the 2W over, and it becomes 800 minus 2W. Now what we're going to do is we're going to take that and we're going to put it into our area formula, since we have a formula for length in terms of width. So let's take that. We're going to take that L and we're going to swap it out for an 800 minus 2W. and then multiply by W. And hey, look at that. Now we have a formula for area all in terms of width. So now we know how to differentiate a function with one variable. So let's do that. Before we do that, we could use product rule if we want, but let's make our lives easy and just expand out first. So 800W minus 2W squared. Then we're going to take the derivative. So that's going to be 800 minus 2 moves out front, and we get 4W. And now if we set that equal to 0, we're going to find the maximum or the minimum. So 800 minus 4W, move the 4W over, and we get 800 equals 4W, where W equals 200 meters. Now, at this point, we're going to skip a couple of steps. Normally, we know that if we're looking for a maximum or a minimum, an absolute max or min, we have to check the endpoints as well. So we could have maybe a width of 400 at the max because we have to fence the two sides. And we could have a minimum of 0. We could have the fence all along the length and use 800 meters of length and have a width of 0 of this thing. But we know that those aren't going to give us any area. And we also know that just by looking at our original formula, that's going to be a parabola that faces down because we have a negative a value. So we know that the part in the middle is the local maximum is going to be the absolute maximum as well. If we didn't, we'd have to test the endpoints. But for this one, we know that width is going to be our maximum. So then we just have to find the length because that's the other part that's asking for. So we're going to take length, and we said it's equal to 800 minus 2W, or 800 minus 2 times 200, or 400 meters. So now we've found the length and the width, so we found everything that the problem is looking for, so we can conclude. Therefore, the dimensions that yield the maximum area are 400 by 200 meters. And it's kind of implied, but just to be safe, I'm going to specify that the first one is the length and the second one's the width. Let's try a different example. So example 2, a piece of sheet metal 60 centimeters by 30 centimeters is used to make a rectangular box with an open top. Find the dimensions that will give the box the largest volume. So essentially we have this piece of sheet metal up at the side here, and we're just going to fold the sides up and it's going to make a box with no top. So we have to figure out what it's asking us for here. So it looks like here it says find the dimensions. So in this case, if it's a box, the dimensions are going to be length, width, and height. So that's what we're going to conclude with. But it's not what we're optimizing. So we have to figure out our optimization keyword, something that talks about something that's really big or really small. So looks like the only one that I see here is the word largest, and that goes with volume. So we're finding the largest volume. So in this case, we're going to find the volume and we're going to optimize it. So we know the formula for volume of a rectangular prism or of a box. It's going to be length times width times height. So in this case, we run into the same problem. We're going to have 3 variables here, and we don't know which one to differentiate. So we're going to have to eliminate some of those and swap them out for something else. So let's use the rest of the information from this problem and use that to help us sort it out. So the first piece of information I see is that it's 60 by 30 centimeters. So let's draw that in right now. The piece of sheet metal all the way across is going to be 60. All the way down is going to be 30. That seems like all the pertinent information here. The fact that it has an open top is important, but we can't really draw that in our diagram. It's already kind of there. So let's draw in our length, width, and height just so we have those. So in this case, the length is the inside length, not the whole thing. It's not the 60. And then the width is going to be the inside width. not worrying about the other ones because they'll be folded up. And then the height's going to be just that little bit there. I'll just draw them all inches so we can visualize it a bit better because they're all the same, right? They're all heights. So we're just gonna fold them all in. So when we look at that, we can actually write a few expressions here that will help us out. We can write expression for length, expression for width. Now the length, all we're going to do is we're going to take the length of the whole sheet, which is 60, and we're going to chop off one of the bits from either end, which are h units. So 60 minus 2 of those h's. And then we have the width, which is 30, and we're going to do the same thing. We'll chop off 2 of those h's. So now we have length and width both in terms of height, so we could plug those back into our volume formula, and we should get an equation that's all in terms of height. So let's try that. 60 minus 2h, 30 minus 2h times h. Hey, look at that. We got an expression that's all in terms of height. So now we have a formula for volume with respect just to height. So now that we have that, we can take the derivative. That's going to get a little bit tricky, so we're going to expand a little bit. You can do the steps on your own. You know how to do them. But to speed things up, I'm going to skip ahead using my Mathemagic here. We have 1800h minus 180h squared plus 4h cubed. So now we have a formula that's expanded. Now we can take the derivative. Let's differentiate that term by term. It's going to be 1800. Then the 2 moves out, it multiplies with 180 to get 360 times h. And then we have the 3 moves out front and multiplies with 4, and we get 12h squared. So now that we have that, now we can take that, set that equal to 0, and that should tell us where our maximum or minimum values are. So in this case, looks like we can common factor this, so it's going to be 12 times 150 minus 30h plus h squared. Now you can try and factor that if you'd like, but I will tell you that this one is not factorable, so we're going to have to use quadratic formula on this. So we're going to use let's see, negative b. In this case, remember that these are flipped. So that's going to be negative b is going to be positive 30 plus or minus b squared negative 30 squared minus 4ac all over 2a. If you do this correctly, you should get 6.34 or 23.66. So those are 2 possible heights that we could have. But I'm seeing a problem here. Take a look at our width. Looks like we only have 30 centimeters of play here, so we can only get rid of 15 centimeters. Our maximum height is 15 centimeters. We could only, the height could only go from 0 to 15. So that's going to be inadmissible. And 6.34 is going to be our only option here. So just to make sure, we're not sure if this is a maximum or a minimum, and we said that the endpoints could be potential absolute maximums and minimums. So we're going to just test all the critical points. So we're going to test h equals 0, h equals 6.34, and h equals 15. And we're going to see what the volume gives us. So let's see. The length is going to be 60 minus 2 times 0, which is just going to be 60. Then we're going to have 30 minus 2 times 0, which is going to be 30. And then the height is going to be 0, so that's going to be 0. So that's going to be equal to 0 centimeters cubed. For the next one, we're going to have 60 minus 2 times 6.34, which is going to be 47.32. Then the width is going to be 30 minus 2 times our height. By the way, these were just those expressions that we found up next to the diagram, if you're looking for them. And that's going to work out to be 17.32. Then the height is going to be just 6.34. So that gives us approximately 5,196 centimeters cubed. Now we just need to test 15 and see what happens there. So 60 minus 2 times 15, that's going to be 60 minus 30, or 30. Then we have 30 minus 2 times 15. That's just going to be 0. So hey, we already know that this is going to work out to be 0, so let's just finish this off really quick. So we know this one is going to give us the maximum. So therefore, and remember, we're concluding with the dimensions, not the area. We don't care about the area, we just care about what dimensions will get us there. Therefore, the dimensions that will yield the greatest area are, let's see, length is going to be 47.32 centimeters. The width is going to be equal to 17.32 centimeters. And the height is going to be equal to 6.34 centimeters. And that's all there is to that problem. Let's try one more before we leave this video. By the way, so depending on the year that I taught this, sometimes I taught this as one lesson, sometimes I taught as two. But considering that we don't need to fill a 75-minute period on this, I'm going to split it up into 2 videos. So we'll post a second video with a few more problems to give us a bit more practice. So example 3, an open-top toy box with a rectangular base is to have a volume of 400 meters cubed. The length of the box is twice its width. The sides of the box will be made of aluminum, which costs $6 per meter squared. But the bottom will be made of tin, which costs $2 per meter squared. Determine the dimensions of the box that will maximize the cost of the materials. So as we're going through this, first thing we need to figure out is what's the problem asking for? It's asking for the dimensions of the box. So again, length, width, and height. But we're also trying to figure out what we're optimizing here. It says that we have to minimize the cost. So trying to figure out the cost of the materials. Actually, as it turns out, this is partly a business problem. So hopefully you business people in the audience will enjoy this. So we're going to have to figure out a formula for cost, and then we can optimize that. So to do that, let's just draw a quick diagram here. We have, let's see, let's just make our net diagram in this one. In this one, we're just going to have something like that. And we said that we're going to find, let's see what information we have here. The volume overall is 400 meters cubed. And the length of the box is twice the width. Here's the length and the width. And we said that that can be written as 2W. So let's see. It's really hard to try and figure out a formula for cost right now. We could, yeah, let's see what we can figure out here. So let's see. Let's start by plugging in 400 equals length times width times height. And we said that length is equal to 2 width. So 2 width times height equals 400. So 400 is going to be equal to 2w squared h. So now we can move over the 2w squared and divide it out, which is equal to 200 over w squared. So that helps out a little bit. So let's move that and give ourselves a bit more space here. It'd be nice if you could do this with pencil and paper. Let's move that over here and let's move that over here. Okay, so to find cost, we're going to have to figure out each of these. Let's call this side 1, this side 2, and we're going to call this B for bottom. So, actually, you know what? Let's call this area 1, area 2, and area bottom, just to help us out a bit. So the cost of this is going to be, we said that the sides cost $6 per meter squared. So we're going to take 2 of those A1s and 2 of those A2s, and that's the amount of material that we need to build the sides, and we're going to multiply it times 6. And then we're going to add on to that $2 per meter squared times the area of the base. I'm just going to rewrite this so that way it's consistent. The areas are up front and the costs are next to them. So now that's going to be equal to 12 times A1 plus 12 times A2 plus 2 times the area of the base. So let's try and rewrite this a bit. Now we have, let's see, A1, that's going to be the width times the height. Area 2 is going to be the length times the height. And the area of the base is going to be length times width. But there's a couple things we discovered here. We said that the length is equal to 2w, and we said that h is equal to 200 over w squared. So let's plug those in and see if we can use that to help us simplify. So 12w, h we're going to do 200 over w squared. And then for length we said 2w. For height we said 200 over w squared. And then we said for length 2w over, or times width, we're going to keep the same. Now that we have that, let's simplify a bit. So let's see, that's going to be, the first one is going to be 12 times 200 is 2400, I believe. Yep, 2400. And w over w squared is going to be over w, which we can also write as w to the negative 1. And then we have, let's see, that's going to be 12 times 2 is 24 times 200 is 4800. And then we have w over w squared, so that's going to be divided by w, or w to the negative 1. And then we have 4 w squared. So when we put that all together, it becomes 4w squared plus 7,200 times w to the negative 1. So now we have a function that represents our cost all in terms of the width. So we can differentiate that now, since we all have all one variable. So let's take the derivative. That's going to be 8w. And then let's see, the next part, the negative 1 is going to move out front and make it a minus 7,200 times w to the negative 2. So now that we have that, let's try and solve by setting it equal to 0. So 8w minus 7,200 w to the negative 2. Just to make this easier, we don't like that exponent negative 2, so let's multiply both sides by w squared. And we get 0 equals 8w cubed minus 7,200. So we move the 7,200 over. 8w cubed. Divide that out, and we get 900 equals w cubed. And that's, when we do the cube root, that works out to 9.65. So in this case, you could also test the endpoints, but if you want, the other way that you could try and solve this, just to confirm that this is an absolute max, a minimum cost and not a maximum cost that it gives you, is that we could make a factor table to test it. So we can test x is less than 9.65, just like we did with curve sketching. X is greater than 9.65, and we're just going to test that derivative. So 8w minus 7,200 over w squared. And we're just going to pick a test value for each side. Let's say we could do x, we should say w, sorry. We do w equals 0 and w equals 10. And when you plug those in, you're going to find that we get a derivative that's negative on one side and positive on the other. So that means that we're going to be negative positive, which means we're decreasing and increasing. So it means that we have a minimum for our cost in the middle. So it confirms that for this function, this is a local minimum, so it's going to work for us. So therefore, the minimum, actually before we do the therefore statement, we haven't found all of our information yet. We found our width, so we need to find a length and a height. So he said the length is going to be equal to 2 times the width. So we multiply that by 2, and then we get 19.3 meters. And for the height, we're going to take 200 over the width squared, and that works out to 2.15 meters. So, lastly, we can conclude with the therefore statement. Therefore, the dimensions that minimize the cost are length 19.3 meters, width 9.65 meters, and height 2.15 meters. So that's pretty much it. Very, very similar to regular problem solving, a little bit trickier. Just remember, always start by asking yourself, what is the problem asking you for, and what are you optimizing? And from there, it should be easy to start trying to figure out a formula, an equation with one variable that will help you to differentiate and solve. So make sure you try some of those practice problems. I will publish one more video with a couple more problems just to help out a little bit more. Happy practicing. Take care.